Hello and welcome to the Black Belt session on monitoring and debugging containerized system. I am personally very interested in hearing about details myself. Our speaker today is Jana Dugan. She's a software engineer at Google. Her favorite piece of software are the tiny games that she used to write for her ZX Spectrum. I had to look it up. It's an 8-bit microprocessor that was released in 1982. She used to know about the Spectrum from end to end, right from the high-level aspects of the system to down to the computer architecture. Nothing would ever give her the same feel as the ZX Spectrum games that she wrote. Her favorite language is Golang, and she worked in that team for 5 years developing Go. I asked her what any interesting facts about her, and she said that she used to see herself as a message in the systems that she maintains in her dreams. That's how she used to diagnose issues in early days of her career and discovered that there are actually tracing tools to do that. This is her first DockerCon, and we would love for you to keep coming and presenting at DockerCon. Take it up.
Thanks a lot for having me. Hello, everybody. I'm Jana, and thanks for coming because this is an afternoon talk, and I was not expecting to see this many of faces. And I just generally came here to actually talk about, new approaches in monitoring and debugging systems. So most of our systems are becoming, more containerized, and container identity, locality, networking, and scheduling is actually becoming huge pieces of the entire big picture. So, but to be honest, all the concepts I will explain here can be applied to just non-containerized systems as well. So a little bit of introduction about me first. I'm an overly frustrated engineer. I've been this is my pretty much 15 year, and I was mainly working on networking systems. My job was mainly to, just figure out how we scale our development as we grow up in the organization and how we scale our work and reliability in production. And my current job is just mainly about making systems more reliable at Google. And this talk is more of a personal story also. So when I decided to give a talk on this topic, I put monitoring as a title because I needed something that people can relate to. But actually what I will talk about here is kind of stuff that is really replacing conventional monitoring. And it's not about observability. This is just one aspect of observability. It's, I just want to give you a little bit of what is going on in the current world. So systems are growing. Most of our systems really start small and, add up to add some complexity over time. Even if you have a controlled size project, you may actually growing up in terms of complexity because your dependencies are growing, right? You're dependent on all these different layers and layers of software and hardware as well that keeps adding up to the complexity. This is what it looks like nowadays. Anything, above the libraries is your user space. And anything above it is just, above it is your user space. Anything below is all this infrastructure you're dependent on. And tons of, new layers are invented and destroyed pretty much on a daily basis. 5 years ago, there was no, Docker or Kubernetes pretty much. I don't know how many years it's been, Docker has been around, but everything is just kind of changing. And what I mean by, we hardly ever understand bare metal. Kernel is super complicated to understand. Networking is such a huge issue, and there are lots of bugs as well. And cloud stack is where I put all these schedulers, container stack, and other high-level components like load balancers and so on. So then what to do? The first strategy, we're always talking about hey, delete all the code. Let's delete. If we cannot delete, we can always rewrite. We can just simplify the things. Don't get me wrong, I'm totally on board with this idea, but it's not that simple. Some problems are really hard in nature, so you cannot just simply delete or advocate for rewriting systems just to minimize the complexity. The bad news is the complexity is inevitable. It's about to be here for a while. And, if we cannot really reduce complexity, what can we do about it? Maybe we need different ways to deal with it, right? Maybe better concepts and tools to understand our systems and to be able to react when things go wrong. Or generally just to understand even when things are going right. So you think that life is amazing and simple when you have this like one single container. This is my perfect world. At this level, problems are really well contained, boundaries are well set. You have all the dependencies and everything you need in that container. I love this abstraction also, like, in this isolation level. It just like looks pretty elegant and clean. And you have several tools already, to diagnose issues with a singleton. You can really depend easily on this, Linux perf tools and diagnostic tools. I'm not sure, if you have used any of this. How many people actually know anything about these tools and using them on a daily basis? There you go, yeah. TCP dump, NetStack, typical DNS diagnostic tools as well, and perf tools as well. But then what happens? It's never as simple as having just one singleton around, because at some point you want to have two containers, and it changes everything. And maybe some networking, right? Because if you have two containers, you need to talk to each other. So I simplified the situation here by limiting it to only two containers. But imagine you have this whole long chain of containers talking to each other, depending on each other, and working in isolation, but still dependent on each other. And the communication among them is just going to vary, right? Regular networking could be one of them. Higher level messaging components like message queues makes things more complicated. And you may have a variety of different things actually triggering different work. And then storage comes into play, and storage is where things get really funky, because storage is the root cause of all the hard problems in terms of both failure and latency, especially when storage is geo-replicated. The geo-replicated writes are such a huge dense, and things may fail very easily. And occasionally, networking is getting so complicated because we have all these funny actors around, load balancers. You're sometimes going out of your local network and, coming back in. Or even in the same network, you're talking to each other through a load balancer. And load balancers are having all these, magical things like making decisions for us and, doing retries or rejecting bad requests and, all the stuff that you don't want to know about. When I containers in the boxes, it looked pretty simpler, but these are actually living in, real hosts. And these host machines are sometimes virtualized, sometimes they're bare naked, run on bare metal, which is less likely. Or there are some extreme cases. These VMs are actually running on other VMs and other VMs. So there are endless number of failure modes, because when you're doing networking and so on, you're, going through all these different bridges to go outside, and as well as when you're coming back in. So the other thing I actually want to talk about before ending up this big series of failure mode is the orchestration, because in the end of the day, all this stuff is orchestrated somehow with the helps of our container schedulers now, whether it's Kubernetes or anything else. And who knows what orchestration does, to be honest. For example, who understands Kubernetes end-to-end? I've been talking to a lot of engineers on the Kubernetes team, and they were telling me that hey, this customer just ended up being in this state, and we don't know why, because we don't know what it triggered, what triggered, and we ended up being in this state. So even people working on infrastructure doesn't understand what their infrastructure is doing. And, who knows if orchestration can actually propagate its decisions end to end. It's so complicated. You see, different components failing in isolation, and nobody understands why and how. So were these problems unique to containerized systems? I don't think so. Because, most of the issues have been around for a long time. But I think containers and the schedulers kind of amplified a bit of our challenges. I think the main areas of issues are coming from this we don't have a locality. Like everything is, it could be here and there. You cannot really track if it's going to be on this physical machine or there. It's hard to keep track of what is going on because it's what the scheduler is doing. You have now more complicated network, and as I was telling you, all the like bridges in between and the more load balancers we actually inject in our systems. And scheduling itself is a huge problem. And just because we like to containerize everything, I think we are breaking down our monoliths more than ever now, and we have all these different service dependencies. Coming back to these like layers of layers stuff, it's just like too much to learn, right? Like too many layers and all scattered around. Nobody is an expert in all of this thing. And people just claim that they are, you need to understand the whole stack sometimes in order to, but you just end up being the person who is given fake promises if you think that like you can learn this all. There's no way. So I'm not sure if you would primarily identify as a developer or an, how many people actually here like identifying as a developer? And how many of you is identifying primarily as an operations person? Okay, it's kind of like half and half. And I will tell you the truth about myself. I always primarily identified as a developer, and I was always like this. Like I had this attitude, hey, my continuous integration is passing, my job is done here, right? Like I just can go and like work on the next thing. I don't care. Somebody's going to take this and, put it to the prod, and yeah, I mean, occasionally need to help them once in a while, but I actually never cared. But our systems only matter when they are available. So you can't really tell that like, hey, my job is done here because my build is passing. You may, after going to prod, there are a few things that you want to do. You want to, you want to actually first set some rules. What is availability to you? And then you want to monitor your systems because you want to see if they are still working. And you want to alert and, page if they are going down. And you want to be able to troubleshoot, right, at some point. And even if you hand it off to a very traditional operations team where like there are actual real organizational boundaries between teams and so on, they will always come back to you. They may come back to you because troubleshooting may be very hard. And at some point, hopefully, you will be able to fix it. But, look at this mess again, like who has time even to document this? All these different relationships between different containers. You also have, storage in this big picture and, networking and so on. Who will have time to debug this in production, especially when things are going wrong, like it's in the middle of the night. You are shaky and you're stressed and, you have anxiety. Many people end up being the single point of knowledge in organizations because they want to learn everything end to end. But they end up being the single point of failures. If they ever take a vacation, everything goes wrong, for example. So we need a healthier approach. I want to actually introduce you a new old concept. This concept has been around for a while. To give you some context, this is usually what a system looks like in the wild world. Many, different services, storage systems, all living in isolation. But they're talking to each other, as I was telling you. Who cares the health of these underlying services? Your users? I don't think so. They actually don't care. They don't understand what is going on here. What they care is like they are making a request and they want to get a response. They don't know about the implementation details. They don't care if it's going through all these like different services and you're preparing a response. What they care is the health and the availability of their experience. So this is why I think we stop worrying about the health and availability of these like isolated individual services. What we care about is more of like the health and the availability of these critical paths. The blue line here is what a critical path looks like. And the user request comes into the load balancer, going through all these different services, all the way down to the storage. And user, again, don't see this picture, but if we want to troubleshoot our systems, we should be able to understand in the life of a user request what happened. That's why we like to, take a look at the things from the perspective of critical paths. And if engineers can see the critical paths, they can actually see all these like components, involved in a user request that may cause problems or latency. This is kind of like a bird's eye, for our systems. You can actually understand critical service dependencies and, critical user execution paths, to be honest. So there are many tools in critical path analysis, but we use distributed traces. And there are other people, for example, using more of like event collection systems, which kind of gives them the same tools. So a distributed trace is a trace that actually can span among multiple processes. Some of our engineering principles are really based on, discovering critical paths from our systems. And then we want to make these paths reliable. And the next thing we want to do is we want to make them fast enough. And we want to make these paths also debuggable in production, because if a user is complaining about the problem, we should be able to see the whole path end to end. Because software has two expected end states. The first one is failure. I don't know, each and every time I talk to some people and they're like, failure never, is not expected. It's of course expected. I think what is unexpected is you are thinking that it's never going to happen. So you need to be prepared for that. And the other thing is the latency. So according to Jeff Dean, these are the basic latency numbers you should know by heart. That's what he says. And, with larger, self-recovering, more resilient systems, there's a lot more magic going on. Just knowing these numbers doesn't really give you a good sense, because sometimes due to our modern stuff, load balancers are thinking there's additional stuff going on. So it's getting harder again to find out what are the root causes of additional latency. And I really love this recent tweet from Ned Friedman. He says, no customer will ever tell you that an extra 500 milliseconds of latency is your biggest problem, but they will prefer using your snappier competitor. Customers just love to complain about failure. When it comes to latency, that was not my experience. They're always like, hey, something is going wrong, but I can't be sure that, it's not my network, whatever. But they would just go and switch to your, more responsive competitor because it works better for them. So I was recently actually hired to work on a project. And this is not a very sophisticated project because I'm not a very sophisticated engineer. So our company has built this gorgeous Pong server. And it, already is built. It runs on Pong server 6996. It just basically responds to every, ping request with a Pong. It's super creative, A+ creative. I think we're doing a good job. It's a legit business. But the sad part is, nobody has built a client that actually, pings this service. So this service feels very lonely. So that's my job, right? I'll just, write this client now, and maybe we'll push it to prod. So I did my homework before coming here, and I wrote a simple client. What it does is, if you can't read Go, in a for loop, it just logs some, ping, and then makes an HTTP pause to this, endpoint, because I know that they built it for me, so it should just work. And I'm going to log something if something fails, and I'm going to just print the response, and it just takes the, the HTTP body and prints it. And then I'm going to wait for 3 seconds because why not? And so I am a lazy person. That's why I also I have some make files, and I'm just going to run ping. So this is just, I put it in a container already, so it just runs from the image. Oh, so shoot, I think there's already a problem. Well, I can tell that like this looks like an easier, like I think I haven't set up my name server. So, and like as you can see from the logs, it's actually easy because just this was like the first hop, right? Like I tried to make a request, it failed, and I had some sense of like a actionable log, which was great. I actually have another script to run the same thing, which is kind of like the poor people's name server. I'm just passing the host, and now it pins, and I'm expecting a pong, but something is wrong. Something is actually pretty wrong. Like I got an empty response, and when I say ping, it actually got a pong, so it actually worked for once. And again, ping and let's see. Again, like no, empty. Let me take a look at the code, so maybe I can actually see something in the code. So the pong service is here somewhere. Well, this is just so simple, right? Like it just only does pong. There's no actually like empty string or anything. Actually, like I'm feeling happy now because this is kind of like a distributed tracing demo. And we can take a look at the distributed traces to see what was going on. Let me check out the latest one. Oh, so interesting because, I'm not sure if you can see the entire call, but I was expecting that like I was making just one request. It turns out like there's a lot going on here. So there's some load balancer involved as far as I can see, and there's a load balancing the issue and decision. And then my request is being forwarded and it's been sent again. So it's kind of interesting that I was not expecting this to happen. And what I see is here like this looks like it's already a successful request. So you can see that the HTTP status 200. I think this is not what I'm looking for because this actually worked. Let me actually filter by 500 so I can see if we have captured anything interesting. Oh, there we go. So this looks a little bit more different. So we send a request again and load balancer decision have been made. And let me see what actually has happened here. So load balancer is supposed to, figure out a target. There are multiple replicas of the Pong server probably, and it should just like figure out, what is the target. And in this case, it decided to go to this like 101. And then, started to proxy the request. It's just starting to, take the incoming request, put it on wire again, and, sending it to target. But interestingly, this actually fails because there is no such host here. And it tried to, retry the request again and again just to see, if actually it can re-execute the request. Interesting. And ended up failing, and then, I ended up having a 500. But the funny thing is, like, from my logs, I just basically didn't see anything at all. Without this level of like instrumentation, I would be not able to see what was going on. Because actually, going back to my ping, now I realize that I handled the error case here, but HTTP status errors are not like handled by the returning error. So client post is never going to return an error if you executed the request and it returns you a non-200 error code. What I should have done is like here and there else, if response status code, maybe HTTP status, okay? If it's different from 200, maybe log something or something. So, in a couple of like seconds, I actually was able to realize that there is something wrong with my code, and was able to see things more, end to end. The other thing I realized is like there's a load balancer in between, right? Like I didn't know about that. Nobody actually told me that there will be I will go through a load balancer. And the other thing is it was retrying. My load balancer was trying to go to a target that doesn't exist. Maybe my load balancer have some bugs. So it was really easy to see. Even though it's a simple ping pong server, things are sometimes complicated. Going back to my slides, I A while ago, we open sourced this like instrumentation tool, and everything that you actually have seen, the data was coming from here. And this is now a project like co-contributed by several companies, Google, Microsoft, Pivotal, the entire Zipkin community pretty much. Signal Effects, Honeycomb, Datadog, and some more people. Like, I don't want to list everybody because there are too many. And we are trying to actually build some instrumentation libraries that are a little bit more holistic. I should only demonstrated the distributed tracing part of it, but it's actually trying to do more. It's trying to also collect metrics, and it's trying to also provide some correlation between different signals, such as metrics and traces and logs. So if you have a latency dashboard, you will be able to see some example traces. And if you have, if you already have a trace in the current context, you should be able to see all the logs that happens, because you already collect so much data in forms of other things, and we want to be able to correlate those signals. So distributed tracing is a cross-stack debugging tool. It's really useful because it allows you to tell you, like, there's a failure, okay, but which specific team is it? Is it me? This is kind of like a Git blame for production, right? Like, we've been able to tell, hey, this specific load balancer issue is not my team's fault. So I can actually, escalate it to the load balancing team really easily with confidence. Especially if you're, running your stuff on a cloud provider, it might be amazing if infrastructure was exposing you this type of spans. So what you can do is like, escalate it to their SRE with confidence. Hey, I got you. This is your problem. And if there's an unexpected latency or something, we just want to be able to see the source code first, maybe. We just want to take a look at what is going on here. And it would be really nice if you just click on this and we build some UI integrations maybe, you just click on this and it takes you to the source code, because it actually knows what handler it's coming from. It might be possible to do that mapping, but no work has been done yet. The other thing is who the page, right? I need actually, so okay, I understand this is a specific team. I understand it's not my fault, but who is the actual person for that? I wouldn't be nicer that you just click on it and it pops up this page, hey, this is the primary on-call person, these are the contacts, whatever, and you can really, engage with them really quickly. So the escalation path is really swift and quick. And often, as I told you, often distributed tracing is one of the signals we collect. We already have other signals around, and wouldn't it be nice to just be able to retrieve other things? Like if I just click on this, give me all the logs. If you have any runtime events, give me all of them. If you have any profiles, give me all of them. So you can actually go, you can easily dig in and try to understand why things are going slow or failing. So distributed traces are just kind of giving you an overview of things. It's not they're not giving you all the details, but they can be enhanced to include more details, such as this case. For example, I have this outgoing request, and what I can see here is when did I get the connection from the connection pool, when did the DNS started, and when it finished, and what was the actual, IP it result. These are really handy when you're debugging things, especially TLS and DNS are the main causes of problems. So you can actually see, all these low-level decisions and events in networking. And this is something that we have done at Google. I actually was reviewing this work. And we can associate now, this is for the Go runtime, but other language runtimes have similar capabilities. And what we can do is we can associate distributed traces with low-level runtime traces. And our SRE was having a hard time understanding what is the root cause of this latency issue. Is it GC, or is it I'm waiting for the scheduler, the runtime scheduler in this case? or I'm waiting on, on a syscall or something. So we can do now a conting. What you can do is like we collect all this stuff. The runtime tracer can follow a distributed trace, and we can actually see what happened in the lifetime of a distributed trace span. And you can say that, hey, in this case, there was this GC pause in this handler again and again. If it's a repeating pattern, what you can do is to go and optimize your allocation maybe for that specific handler. And similarly, you should be able to, see your continuous profiles if you are continuously profiling, and you can actually label things correctly, so you can actually associate the profiles coming from a specific handler. If you're doing some computationally expensive jobs, such as, compression or crypto, profiles are really useful. This is what I did, for example, to diagnose an issue. Here, in this case, there was a generate ID function that was like running in a loop and trying to, generate new IDs, and it was actually, creating, ended up like performing not so well and spending more time on the CPU. We just optimized it, and latency issue is gone. And there's another thing that I want to talk. This is already something that we use at Google, and it's just like, it's been a long time, and like the CSS looks terrible, by the way, but it's a very useful tool. This is an in-process data report. So all the servers at Google expose some dashboards, in-process dashboards. If you go to a server at Google to some port /traces, you will see a page like this. What this does is actually like giving you all these like different spans collected in a specific process. And you can actually see, different latency samples. There's a latency, you can see the latency buckets, right? Like there are several samples, and you can see all the, the annotations and everything. If there's an error, you can also see the error spans. This is so useful. If we cannot like upload our data to the tracing backend, we just go to this endpoint and see what happened. This is kind of like a last resort for us. And what we want to do is to provide some cluster container-wide first and cluster-wide dashboards. So without really relying on anything else, you can just, just like run it and like start collecting data inside your container, or, cluster-wide, such as like your Kubernetes cluster. So I want to explain some of the challenges, because there are a few challenges, and I think distributed tracing just is not becoming a mainstream tool because of these challenges. The first one is, if you need distributed traces, it becomes a cross-team problem. As I was showing you the tree of traces, and in order to construct that tree, you need to propagate some identifiers around. So all these like different blocks, bars, were coming from different processes, and in order, for distributed tracing backend to, put them all together, you need to propagate the identifiers around. And unfortunately, there's not a very well, industry standard for this yet. All the providers are providing their own identifier format and the header format. But the good news is like there's an upcoming proposal to W3C, which I also helped. This is a draft at this point, but we are actually starting to adopt it. And there will be a canonical trace HTTP header. And it will be so cool, because just imagine like the entire stack, all the web frameworks and HTTP clients and everyone else. So we will go to them and like tell them like, hey, honor this header. If you can't do anything about it, just pass it. Because you want to have, like end-to-end traces, not just like some broken stuff because you haven't passed the right header. And this is, you don't have to learn about this header at all at this point, but this is currently what it looks like. And the header name is trace parent, because you actually propagate the parent identifier, and then you create some children if, you are doing more work derived from that parent. It's just basically several identifiers and some options. And similarly, we don't have a standard for data export, and there's no real mechanism for like export at this point. What we do in our instrumentation libraries right now is just like linking some exporters inside the process, so it uploads data to the tracing backend. But this is really hard, especially if you have pre-built binaries. Like imagine you have a web server, you get Nginx, and you just want to configure it and like make it write traces to somewhere, maybe in a good well-known format, so I can exchange it and like upload it to somewhere else. So this is still being an issue, and there's not a lot of work going on here, but I hope that we will get to this in a year or so. So distributed tracing is not magic, but I think like it's kind of like, it actually closes knowledge gaps more than any other tool if it's set up properly. And going back to this like specific issues, challenges, I think it kind of like addresses, when you have enough traces, it addresses all the challenges that just have been amplified in the modern time. You can figure out the locality because you can collect, I haven't shown you in the demo, but you can collect the actual physical location of the span, the network policies it's using, and so on. So you actually have a sense. And, it can capture scheduling if scheduler can contribute to the user traces, which is something that we are trying to do with Kubernetes right now, but it's kind of like experimental. And you learn about your dependencies because, your trace itself can tell about the dependencies. So that's all I have today. Thanks so much for having me, and I'm really happy to, answer any questions if you have any. There's also a microphone over there. It would be so nice if you can use the microphone. There are no questions. That's awesome. Everything was crystal clear. Yeah, question. Maybe I can bring you the mic. Yeah, I think I can hear you.
I wanted to ask that, specifically when talking about containers,
yeah.
all the systems that like when we are talking about namespace, Facebook, all the stuff that is inside there, is there a specific tooling that supports the thing that you just asked for that part that is inside there?
I don't know any of that stuff, like any of the specific tools. I'm not sure like if you can actually like use the Linux's some syscall type of tracing support, but it's really hard to associate it with the user, trace. So there are currently no tools, and we need to I think as soon as there is the standard going on, we will have like some different, conversations with people to see if we can associate any of those identifiers with, this type of identifier.
So we should assume that we are in the very same situation.
Sorry, can you repeat that?
We should assume that we are in the very same situation as the other two.
Yeah, we don't have, but as I told you, currently what you can do is it's kind of like an overview. You don't want that much detail maybe, because you can specifically figure out, you have, for example, so many replicas around, you can figure out what specific replica or, place is the root cause of the problem, and then you can go there and maybe SSH and then gather more data and, use other ways of gathering more data and looking at it. Yeah, no problem. There. Can you use the microphone? I can't really truly hear.
So thanks for the talk. What about the really time-critical stuff? So stuff that shouldn't be touched, with or bothered with or slowed down with additional logging and stuff like this.
So the question is, what about really highly, time-sensitive type of work? So I haven't mentioned any of this, but distributed traces are not for really time-critical things. It's adding for example, 10% overhead on top of an RPC already, and what you can do is just have a very optimized collection and export it in a different way. But what people end up doing is downsampling by default. So you don't collect actually tracing for every request. You just gather 10% of it or so on. In Google's case, even for distributed traces, we only trace one of every 10,000 requests, and then you end up actually missing some of the important cases, such as 95th percentile or so on, because it's really probabilistic. And we have like 2 different strategies. So there are actually different levels. Instrumentation itself is costly. Also exporting that amount of data is costly. If you can do the sacrifice of doing instrumentation and locally maybe collect, what you can do is like, take a look at what is interesting and what is not interesting and filter out the interesting parts and like maybe upload the interesting ones. That's why we are interested in working in this cluster-wide collector. So at least in a cluster, which is where the networking is pretty cheap, we will just write all the things down there. But in order to, I think, respond to your question, if it's super time critical, if you cannot, afford the instrumentation, I don't think that like this type of large data is something you want to go with. Okay. You may want to, invent your own tiny footprint type of, instrumentation stack. Yeah.
Makes sense. Thanks.
Cool. All right, no more questions. One more.
How do you deal with the absence of distributed tracing? For example, in the first example, we had the distributed tracing from a load balancer, but if you, for one call, you have one load balancer, which is a new version, which doesn't implement distributed trace ID, and there is no trace ID for this particular call. How do you deal with that absence?
Did I answer it correctly? So what happens, for example, if you deployed a new version of the load balancer which cannot understand the incoming trace ID, you simply end up, dropping the trace. And the best thing you can do is, if you have collected some logs or some stuff, especially with the trace context inside, you can just take a look at that. But like that's the biggest problem right now. We end up using the same trace identifiers all around in the same organization, which requires a lot of work because you sometimes need to basically build everything from source to have that level of control. That's why the standardization is important, and that's the only thing that distributed tracing can be popular and mainstream. Because you end up dropping the distributed trace. There's no answer to, solution to that question. Yeah. All right, thank you so much. Thanks.